Hello, I'm Joey Mireles, and I'll be presenting this video on behalf of Group 3, which includes Frank Lee and myself. I'll be sharing a quick overview of our project, Attacking End-of-Life Satellites. At why end-of-life satellites pose a risk, then go straight into our scenario by going over basic assumptions that we made, the two different attacks we envisioned, and the defenses and recommendations to help prevent this type of attack. Currently, there is a large amount of satellites in Earth orbit, including 3,170 inactive satellites per geospatial world. While Geospatial World doesn't disclose their methodology, the Union of Concerned Scientists confirms 3,000 active satellites, so we can say that the number of inactive satellites is at least a good estimate. BIS research estimates that over 43,000 satellites will be launched over the next 10 years, producing a large number of inactive satellites in orbit around the Earth in that time period. As we see with the Sirius XM satellite example, not every end-of-life satellite is placed in a graveyard orbit away from active satellites. With the situation now set, let's move on to our attack scenario assumptions. These are the assumptions we made for this attack plan. Using the Aerospace Corporation threat matrix, we identified this as a Tier 6 or Tier 7 state actor threat. With this, we can also assume that the threat actors have the required assets to conduct the attack. The threat actor requires knowledge of the spacecraft systems that they are trying to undermine, including software, firmware, and any other subsystem they want to compromise. The most important assumption is that the end-of-life satellites tend to have minimal ground station staffing to monitor the spacecrafts, and that this is the major issue we are going to exploit with our attack. The initial attack begins with a GPS spoofing attack. The threat actor needs to know where the satellite is and where it is predicted to be. Then they will need to ensure that the rogue satellites are in the correct position to spoof the GPS signal. As mentioned earlier, they will require several space assets, at least 4 for the GPS spoofing. This is because any GPS receiver requires at least that many signals to use GPS to find their position. This compromises the satellite's ephemeris data, and if it autonomously corrects its orbit and position, then we can convince the satellite to move into a position that is either disrupting other missions or impacting other space assets. In the case we are unable to convince the target satellite to move, we would move into the second phase of the attack plan. This attack starts with the assumption that the incorrect GPS location causes the satellite to move into a safe mode. Once again, it is assumed that no one is watching or cares that an end-of-life or end-of-mission satellite is in safe mode. We then assume that the designers did not create a crypto safe mode, which means that cryptography and authentication is disabled for uploading new commands or code. We can now inject our own code, enabling regular control of the craft and disabling the safe mode signal, and then start causing real problems. We can override the electrical subsystem by overloading the battery or using the heating system to overheat the propellant or other vital systems. This could possibly cause an explosion, creating a debris field that will disrupt other missions for a long time, as seen in real-world examples as satellite collisions or ASAT tests. Since the threat actor is now in control of the satellite, they can use it for any purpose that they have access to subsystems for and the imagination to plan for. We used the Sparta technique tree to determine effective countermeasures for these attacks. First and foremost, you must protect your sensitive information. This prevents threat actors from being able to plan cyber attacks because they are unaware of how to compromise your system. A specific countermeasure for GPS spoofing is a redundant position determination, including physics-based verification of positions. For safe mode countermeasures, the most important is to ensure all spacecraft have a cyber safe mode, which preserves the need for encryption even in safe modes, and to restrict the spacecraft from receiving certain commands unless certain conditions are met first. Our recommendation overall for this scenario is to shorten the time between end of mission and deorbiting, possibly by having deorbit strategies prepared and approved before end of mission to ensure that there are not many targets in space for threat actors to compromise. This concludes our presentation. We hope you enjoyed it and have learned more about cybersecurity and space systems.